The Fabric of the Cosmos by Brian Greene. Have you ever looked up at the night sky and felt a profound sense of wonder, maybe mixed with a little bit of insignificance? The sheer scale of it all, that endless darkness dotted with impossibly distant lights. It's a feeling that connects us to our earliest ancestors, who gazed at those same stars and asked the same fundamental questions. What is all of this? Where did it come from? And what is my place in it? For most of human history, these questions belong to philosophers and poets. But, over the last few centuries, a handful of brilliant, stubborn, and endlessly curious minds have begun to pull back the curtain on reality itself. And what they've found? It's stranger, more beautiful, and more mind-bending than any science fiction story ever conceived. Today, we're diving into one of the most important books ever written on this subject, The Fabric of the Cosmos by Brian Greene. This isn't just a book. It's a guided tour through the very texture of reality. Since its publication, it has sold millions of copies and earned recognition as a masterpiece of scientific storytelling, solidifying Brian Greene's reputation not just as a brilliant physicist at the forefront of his field, but as one of the greatest scientific communicators of our time. Greene's journey into these questions began, funnily enough, not with a telescope but with a philosophy book. As a teenager, he stumbled upon Albert Camus' The Myth of Sisyphus, which opens with the startling line, "There is but one truly philosophical problem, and that is suicide." Camus argued that before we ask any other question about the nature of the universe or the categories of the mind, we must first decide if life is worth living. While the young Greene was struck by this, he couldn't shake a feeling that something was missing. How could we possibly assess the value of life without first understanding the arena in which it's played? What if our senses, our everyday experiences, were giving us a completely flawed picture of reality? What if we were like beings living deep in an underground cave who had never seen the sun, the ocean, or the stars? Our assessment of life would be profoundly incomplete. This is the promise of Brian Greene's work. He takes us on an astonishing ride, from the familiar world of falling apples and spinning buckets to the farthest reaches of space and the earliest moments of time. He shows us that the reality we experience every day is just a thin, delicate veil draped over a cosmic fabric that is richer, deeper, and stranger than we can imagine. By the end of our journey today, you'll understand that space isn't empty, that time doesn't truly flow, and that the past isn't as set in stone as you think. You'll see how the universe itself may be just one bubble in a vast cosmic foam of other universes. And most importantly, you'll come to see the world not as a collection of separate things, but as a deeply interconnected, unified whole. This isn't just about physics. It's about understanding the fundamental stage on which our lives unfold. It's about coming of age in the cosmos. Our story begins with a deceptively simple object, a bucket of water. Imagine you take a bucket, fill it with water, and hang it from a rope. You twist the rope tightly and then let it go. At first, the bucket spins, but the water inside stays still, its surface perfectly flat. But then, friction kicks in. The spinning bucket gradually coaxes the water to spin with it. And as the water starts to spin, something curious happens. Its surface curves. It becomes concave, climbing up the sides of the bucket. Now, why does this happen? The simple answer is that the spinning forces the water outward. But the great Sir Isaac Newton, who first described this experiment over 300 years ago, was after a much deeper question. He asked, spinning relative to what? This question might seem trivial, but it opens a rabbit hole that leads to the very nature of space and time. You might say the water is spinning relative to the bucket. But Newton pointed out that this can't be right. At the very beginning of the experiment, the water isn't spinning relative to the bucket, yet its surface is flat. A moment later, when the water is spinning with the bucket, there's no relative motion between them, yet the surface is concave. The bucket itself can't be the reference point. So what is it? Newton made a bold and brilliant leap. he proposed that there is an absolute reference frame for all motion, an invisible, unchangeable, universal stage upon which all the events of the cosmos play out. He called it absolute space. According to Newton, the water's surface becomes concave because it's accelerating relative to absolute space. When you're in a car that takes a sharp turn, you feel pressed against the door because you're accelerating relative to absolute space. This idea became the bedrock of physics for 200 years. It was clean, it was powerful, and it worked. Space was a fixed, eternal, absolute entity. Time, too, was absolute. A universal clock, ticking away at the same rate for everyone, everywhere. This was the classical reality. It was a universe like a grand clockwork machine, set in motion at the beginning and ticking along predictably, governed by unwavering laws on an unchanging stage. But not everyone was convinced. Newton's rival, the German philosopher Gottfried Leibniz, argued passionately against this idea. He said that space isn't a thing in itself, it's just a system of relationships. To say space is just a convenient way of describing the distances and directions between objects. If you were to remove every object from the universe, Leibniz argued, the very concept of space would become meaningless, like an alphabet without any letters. This is the relationist view. For 2 centuries, Newton's view held sway, but Leibniz's objection lingered in the shadows. It took another brilliant mind, the Austrian physicist and philosopher Ernst Mach, to revive the debate. Mach looked at Newton's bucket and asked a simple question. How do you know what would happen if the experiment were done in a truly empty universe? In our universe, when the water spins, it's not just spinning relative to absolute space. It's spinning relative to the Earth, relative to the Sun, relative to the distant stars and galaxies. Mach proposed that it's the gravitational influence of all the matter in the universe, all those distant stars, that provides the true reference frame for motion. In a completely empty universe, Mach argued, there would be no distinction between spinning and not spinning. The water in the bucket would remain flat. Your arms wouldn't splay out if you spun around. You would feel nothing. In Mach's view, inertia, the resistance you feel to acceleration, isn't a property of an object interacting with absolute space, but a result of its interaction with all the other matter in the cosmos. This idea, known as Mach's principle, was profoundly influential. It put the relationist view back on the map and deeply inspired a young patent clerk in Switzerland named Albert Einstein. Einstein was obsessed with the idea of relativity. He understood that motion at a constant velocity is relative. If you're on a smoothly moving train, you can't tell if you're moving or if the world is moving past you. But accelerated motion, like the spinning bucket, seemed absolute. You can feel it. This asymmetry bothered him. He was also bothered by another problem. The laws of electricity and magnetism, unified by James Clerk Maxwell, predicted that the speed of light was a constant, 670 million miles per hour. But relative to what? Most physicists assumed light traveled through an invisible substance called the ether, and its speed was constant relative to this ether. This ether was, in essence, a stand-in for Newton's absolute space. But numerous experiments had failed to detect it. In 1905, Einstein took a breathtakingly simple and audacious step. He declared, "There is no ether. The speed of light is constant relative to everyone." This simple statement shatters our everyday intuition. If you're driving on a highway at 60 miles per hour and you turn on your headlights, you'd think the light beams would travel away from you at the speed of light minus your 60 miles per hour. But they don't. You and someone standing on the side of the road will both measure the light traveling at the exact same speed, 670 million miles per hour. How can this be possible? Speed is just distance divided by time. If 2 observers measure the same speed for light, but are moving relative to each other, there's only one way it can work. Their measurements of distance and time must be different. This was the core insight of Einstein's special theory of relativity. He dismantled Newton's absolute space and absolute time. Your experience of time and space is personal. Your clock and your ruler aren't universal. The faster you move through space, the slower your clock ticks relative to someone stationary. The faster you move, the more contracted distances appear in your direction of motion. Einstein revealed that space and time aren't separate things. They're two parts of a single, unified entity, spacetime. Imagine spacetime as a giant loaf of bread. For any one person, now is like a single slice of that loaf. It represents all of space at one instant in time. But for someone moving relative to you, their now is a different slice, cut at a different angle. Your now and their now aren't the same. If you and an alien in a galaxy 10 billion light-years away were stationary relative to each other, you'd share the same now slice. But if that alien simply stood up and started walking away from you at a gentle pace, their slice of now would tilt so dramatically that their present moment could correspond to what you consider to be 200 years in your past. Events that are in your future could already be in their past. So what does this mean for Newton's bucket? In a way, Einstein brought back the idea of an absolute. It wasn't absolute space or absolute time, but absolute spacetime. Even though different observers slice up the spacetime loaf differently, the loaf itself, the entire four-dimensional block of spacetime, is the same for everyone. Acceleration, Einstein showed, isn't motion relative to absolute space, but curved motion through absolute spacetime. So even in an empty universe, the water in the bucket would curve because it's following a curved path through spacetime. The pendulum swung back from Mach's relationism toward a new kind of absolutism. But Einstein wasn't finished. Special relativity was a theory of constant velocity motion. It didn't include gravity. For the next 10 years, Einstein grappled with how to fit gravity into this new picture of spacetime. He was also still deeply inspired by Mach's idea that matter should determine the structure of the universe. One day, he had what he called his happiest thought. He realized that the feeling of gravity is indistinguishable from the feeling of acceleration. If you're in an elevator that starts accelerating upward, you feel pressed to the floor, just like gravity. If you're an astronaut in a rocket accelerating through empty space, you would feel a force that's identical to gravity. Conversely, if you're in an elevator and the cable snaps, you and everything in the elevator would be in free fall. You would feel weightless, as if gravity had vanished. This is the principle of equivalence. Gravity and acceleration are two sides of the same coin. This led Einstein to a revolutionary conclusion about the nature of gravity. Newton saw gravity as a force pulling objects through space. Einstein realized that gravity isn't a force at all. It's the curvature of spacetime itself. Imagine a stretched-out rubber sheet. If you place a bowling ball in the middle, it creates a dip. If you then roll a marble nearby, it won't travel in a straight line. It will follow the curve created by the bowling ball. The marble is simply following the straightest possible path on a curved surface. This is exactly how gravity works. A massive object like the sun doesn't pull the Earth. It warps the fabric of spacetime around it. The Earth in its orbit is simply following the straightest possible path through this curved spacetime. The planets orbit the sun for the same reason a marble circles the drain in your bathtub. With his general theory of relativity, Einstein had finally given us a true picture of gravity. Spacetime was no longer a passive stage. It was a dynamic, flexible player in the cosmic drama, shaped by matter and energy, and in turn telling matter and energy how to move. And in this picture there was a distinctly Machian flavor. What determines the curvature of spacetime? All the matter and energy in the universe. The path of a single particle is influenced, however minutely, by every other piece of matter in the cosmos. So in a sense, the universe's matter does define the arena for motion. However, the theory wasn't fully Machian. Even in a completely empty universe, spacetime would still exist, flat and featureless, providing a benchmark for acceleration. The debate wasn't over, but it had been transformed. Just as Einstein was rewriting our understanding of the very large, another revolution was brewing that would shatter our understanding of the very small. This was the birth of quantum mechanics. Classical physics, both Newton's and Einstein's, is deterministic. If you know the position and velocity of every particle now, you can, in principle, predict the entire future and reconstruct the entire past. The universe is a predictable machine. Quantum mechanics says this is fundamentally wrong. At the heart of the quantum world is uncertainty. You can never know both the exact position and the exact velocity of a particle at the same time. The more precisely you know one, the less precisely you can know the other. This isn't a limitation of our measuring devices. It's a fundamental property of reality. Because of this, quantum mechanics is a theory of probabilities. It doesn't tell you what will happen, but what might happen. A particle, like an electron, doesn't have a definite location until you measure it. Before that, it exists in a haze of possibilities, described by a probability wave. The wave tells you the likelihood of finding the electron here, or there, or way over there. This led to one of the strangest experiments in all of science, the double-slit experiment. If you fire a stream of tiny pellets, like electrons, at a barrier with two slits in it, you'd expect to see two bands on a detector screen behind the barrier, corresponding to the pellets that went through one slit or the other. But that's not what happens. Instead, you see an interference pattern, a series of bright and dark bands. This is the hallmark of waves. It's what you get when water waves from two sources overlap, reinforcing each other in some places bright bands, and canceling each other out in others dark bands. This means that each electron somehow behaves like a wave. But what is waving? The probability wave. And here's the truly mind-boggling part. You can slow down the experiment so that you fire only one electron at a time. Each electron makes a single dot on the screen. But over time, as thousands of individual electrons hit the screen one by one, their dots build up the same interference pattern. Somehow, each individual electron, traveling by itself, seems to pass through both slits at the same time and interfere with itself. This idea that a particle can have multiple histories, that it can take all possible paths simultaneously, was formalized by the brilliant physicist Richard Feynman. He showed that to calculate the probability of a particle going from point A to point B, you have to sum up the contributions from every possible path it could have taken. This completely rewrites our notion of the past. A single event in the present isn't the result of a single unique history. It's the result of an amalgam of all possible histories. This quantum weirdness deeply troubled Einstein. He famously declared, "God does not play dice." He believed that the probabilistic nature of quantum mechanics was a sign that the theory was incomplete. There must be a deeper, hidden reality where things are definite. In 1935, with his colleagues Boris Podolsky and Nathan Rosen, he devised a thought experiment to expose what he saw as the absurdity of quantum mechanics. This is now known as the EPR paradox. Imagine you have a process that creates two particles that fly off in opposite directions. Quantum mechanics allows for these particles to be created in an entangled state. This means their properties are linked. For example, they could be entangled in their spin. Spin is a quantum property, a bit like the spin of a top. Let's say the particles are entangled, so that if you measure one and find its spin is up, you will instantly know the other's spin is down, and vice versa. Now, here's the catch. According to quantum mechanics, neither particle has a definite spin until it's measured. Each exists in a probabilistic haze of both up and down. So you let the two particles travel light years apart. Then you measure the spin of the particle on the left. Let's say you find it's up. You instantly know that the particle on the right, light years away, must be down. The act of measuring the left particle seems to have instantaneously affected the right particle, forcing it to snap out of its haze and adopt a definite down spin. Einstein called this spooky action at a distance. How could a measurement here instantly affect something over there without anything traveling between them? It seemed to violate the speed of light limit from his own theory of relativity. Einstein, Podolsky, and Rosen argued that the only sensible explanation was that the particles had definite spins all along. They were like a pair of gloves. If you put them in two boxes and mail them to opposite ends of the Earth, you don't know which is which. But if you open your box and find the left glove, you instantly know the other is the right glove. There's no spooky action. The information was there all along. The particles, they argued, must have hidden variables that predetermine their properties. For decades, this was a philosophical debate. It seemed impossible to test. How could you ever know what properties a particle had before you measured it, when the act of measurement itself is what brings the properties into being? Then, in the 1960s, a brilliant Irish physicist named John Bell figured out a way. He devised a mathematical theorem showing that if Einstein was right, if there were hidden variables and no spooky action at a distance, then the correlations between measurements on the two entangled particles would have to obey a certain inequality. If quantum mechanics was right, and the spooky connection was real, that inequality would be violated. It took another couple of decades for technology to catch up, but in the early 1980s, a team led by the French physicist Alain Aspect performed the experiment. The results were unambiguous. Bell's inequality was violated. Quantum mechanics was right, Einstein was wrong. The universe is not local. What happens over here can be instantaneously linked to what happens over there, regardless of the distance separating them. Space, it turns out, doesn't always separate things. Quantum entanglement can weave a connection that transcends space. A particle can run, but it can't hide. Even on opposite sides of the universe, two entangled particles behave as a single unified entity. This is one of the most profound and mind-shattering discoveries in the history of science. It challenges our deepest intuitions about what it means to be separate. So we have these two towering pillars of modern physics: general relativity, the theory of the very large, of space-time and gravity, and quantum mechanics, the theory of the very small, of particles and probabilities. Both have been tested to incredible precision. But there's a problem. They're fundamentally incompatible. When you try to combine them, when you try to describe gravity on the scale of quantum mechanics, like at the center of a black hole or at the moment of the Big Bang, the equations break down. They give nonsensical answers, like infinite probabilities. The smooth, gentle curvature of Einstein's spacetime clashes violently with the jittery, chaotic frenzy of the quantum world. This is the central conflict in modern physics. This brings us to the grand quest for a unified theory, a single framework that can describe all forces and all matter. This was Einstein's dream in his later years, and it's the holy grail of modern physics. The leading contender for this unified theory is superstring theory, or simply string theory. String theory proposes a radical new answer to the ancient question, what are the fundamental constituents of matter? For centuries we thought it was atoms. Then we discovered protons, neutrons, and electrons. Then we discovered that protons and neutrons are made of even smaller particles called quarks. Conventional theory says that electrons and quarks are points, dots with no size at all. String theory says this is wrong. It proposes that if you could zoom in on an electron or a quark with unimaginable magnification, you would see that it's not a point, but a tiny, vibrating filament of energy, a little string. And here is the beautiful part. Just like a violin string can vibrate in different patterns to produce different musical notes, these fundamental strings can vibrate in different patterns. And each pattern of vibration corresponds to a different kind of particle. A string vibrating in one way would have the mass and charge of an electron. A string vibrating in another way would have the properties of a quark. A string vibrating in yet another way would be a photon, the particle of light. Even the graviton, the particle that transmits gravity, would be just another vibration of the same fundamental string. In this picture, the entire universe, with its rich diversity of particles and forces, is like a grand cosmic symphony. All the different particles are just different notes, played by a single entity. The string, This is the ultimate unification. But how does this solve the conflict between general relativity and quantum mechanics? The key is that strings aren't points. They have a tiny but finite size, roughly the Planck length, about 100 billion times smaller than an atomic nucleus. This tiny size is the secret. The violent quantum jitters of spacetime that cause the infinities in the equations happen at distances smaller than the Planck length. Since strings are the smallest things that exist, they can't probe these infinitesimal distances. They effectively smear out the quantum chaos, calming the jitters and resolving the conflict. String theory, for the first time, provides a consistent quantum theory of gravity. But it comes with a shocking prediction. The mathematics of string theory only works if the universe has more than the 3 spatial dimensions we see. In fact, it requires 9 spatial dimensions for a total of 10 space-time dimensions. A more recent, unified version called M-theory requires 10 spatial dimensions, or 11 space-time dimensions. Where are these extra dimensions? The idea, which goes back to the 1920s, is that they're curled up into a tiny, complex shape tacked on to every point in our familiar 3 dimensions. Imagine a garden hose. From far away, it looks like a one-dimensional line. But if you get close, you see it has a second, circular dimension. The extra dimensions of string theory are like that circular dimension, but curled up to an unimaginably small size, far too small for us to see. These tiny curled-up dimensions aren't just a mathematical curiosity. Their precise shape and size determine the possible vibrational patterns of the strings. And since the vibrational patterns determine the properties of the particles, their masses, their charges, the geometry of the hidden dimensions dictates the fundamental laws of physics we see in our world. The answer to why the universe is the way it is may be written in the shape of these extra dimensions. This brings us back to the beginning of everything, cosmology. The standard Big Bang theory describes the universe as expanding and cooling from an incredibly hot, dense state about 14 billion years ago. It explains a huge amount of what we observe, but it has some deep problems. One is the horizon problem. The cosmic microwave background radiation, the afterglow of the Big Bang, is incredibly uniform in temperature across the entire sky. This means that regions of the universe that are now on opposite sides of the sky and have never had time to be in contact with each other somehow knew to be at the same temperature. Another is the flatness problem. According to general relativity, the universe can have one of 3 shapes: positively curved like a sphere, negatively curved like a saddle, or flat. Our universe appears to be incredibly close to flat. But for it to be so flat today, it must have been even more fantastically flat at the beginning. The standard Big Bang theory offers no explanation for this exquisite fine-tuning. And finally, the Big Bang theory doesn't explain the bang itself. What caused the initial outward expansion? Gravity is attractive. It should have caused everything to collapse, not expand. In the 1980s, a new idea called inflationary cosmology proposed a stunning solution to all these problems. The idea is that in the first fraction of a second after its birth, the universe underwent a period of hyper-fast, exponential expansion. A tiny patch of space, far smaller than a proton, swelled to a size larger than the entire observable universe today, in less than a trillionth of a trillionth of a trillionth of a second. This incredible burst of expansion was driven by a form of repulsive gravity. Einstein's equations show that if space is filled with a particular kind of energy field, called the inflaton field, it will have a negative pressure, which creates a powerful outward gravitational push. Inflation solves the horizon problem because the entire observable universe we see today originated from a tiny causally connected region before the inflationary burst. Everything had time to reach the same temperature before being stretched to cosmic scales. It solves the flatness problem because the colossal expansion would have stretched any initial curvature into near-perfect flatness, just as inflating a tiny wrinkled balloon to the size of the Earth would make its surface appear perfectly flat to any observer on it. And it explains the bang. The inflationary burst was the bang, a stupendous, gravitationally repulsive explosion that set the universe on its expanding course. But perhaps the most profound achievement of inflation is that it provides a source for all the structure we see in the universe, the galaxies, the stars, the planets. It does this through quantum mechanics. Even in what we think of as empty space, quantum uncertainty ensures that there are tiny, random jitters, quantum fluctuations. During inflation, these microscopic quantum fluctuations were stretched to astronomical sizes. These tiny variations in energy density became the seeds around which matter later clumped, forming the galaxies we see today. The galaxies, the stars, the diamonds in the sky, they're all quantum mechanics writ large across the cosmos. This brings us to the final, deepest puzzle, the arrow of time. Why does time seem to move in one direction? Why do we remember the past but not the future? Why do eggs break but never unbreak? The fundamental laws of physics, from Newton to Einstein to Schrödinger, are time-symmetric. They work just as well forward as they do backward. A movie of a planet orbiting a star would look perfectly normal if you ran it in reverse. The answer lies in entropy, which is a measure of disorder. The second law of thermodynamics states that the total entropy, or disorder, of a closed system always increases over time. A whole egg is a low-entropy, highly ordered state. A splattered egg is a high-entropy, disordered state. There are vastly more ways for the atoms of an egg to be in a splattered mess than in the precise configuration of a whole egg. So it's statistically almost inevitable that things will move from order to disorder. This explains why eggs splatter, but it creates a deeper puzzle. If entropy always increases, it means the universe must have been in an even more ordered, lower entropy state yesterday than it is today, and even more ordered the day before that. Following this logic all the way back, it means the universe must have begun in a state of almost perfect order, of incredibly low entropy. The puzzle of the arrow of time becomes the puzzle of the initial state of the universe. Why did the universe start in such an improbable, highly ordered configuration? Inflation provides the answer. The inflationary burst smoothed out the universe, wiping away any initial lumpiness or disorder. It created a vast, uniform, homogeneous space, populated by a smooth bath of particles. This was an incredibly low entropy state. It was like winding up a cosmic clock. For the last 14 billion years, the universe has been unwinding, with entropy steadily increasing, as gravity has pulled matter together to form the rich, complex structures we see today. The arrow of time, the one we experience every moment of our lives, was forged in the fire of that initial inflationary expansion. We've come a long way. From Newton's absolute stage to Einstein's dynamic spacetime, to the probabilistic, entangled, and multi-dimensional world of string theory, our picture of reality has become richer and more complex with each step. We've seen that what we call empty space is a boiling cauldron of quantum activity. What we call time is a personal experience that doesn't flow in any universal sense. And what we call the universe may be just a thin membrane, a brain, floating in a higher dimensional reality, perhaps endlessly cycling through collisions with other brains. These ideas are at the very frontier of human knowledge. They're speculative, they're strange, and they push our imagination to its limits. But they're not just wild guesses. They're the logical consequences of our most successful theories, theories that have been tested and confirmed to astounding degrees of accuracy. The quest to understand the fabric of the cosmos is the quest to understand our home. It's a story of constant revelation, of peeling back layer after layer of illusion to get closer to the truth. And it's a story that's far from over. We're still in the jungle, as Greene says, still filled with confusion, still guided by hunches and calculations. But we're moving forward. With new telescopes gazing up at the heavens, and new particle accelerators probing down into the heart of matter, We're on the verge of the next great leap in understanding. As we step back from this incredible journey, what are we left with? What's the central lesson from the fabric of the cosmos? For me, it's a profound lesson in humility and wonder. The reality that Brian Greene paints is one where our everyday experience is a beautiful but ultimately limited slice of a much grander and stranger whole. Think about it. Our senses evolved for survival on the plains of Africa, not for comprehending the quantum jitters of empty space or the 10-dimensional geometry of string theory. It's a miracle of the human mind that we can even begin to grasp these concepts. Greene shows us that the universe isn't just out there, it's in us. The arrow of time that governs our lives, from birth to death, is a cosmic arrow, set in motion by the conditions of the Big Bang. The very matter that makes up our bodies, the carbon, the oxygen, the iron, was forged in the hearts of stars that lived and died long before the Earth was formed. We are, quite literally, stardust, and the laws that govern the smallest particles within us are the same laws that govern the largest structures in the cosmos. There's a deep, underlying unity to everything. This book reminds me that the most powerful tool we have isn't a telescope or a particle accelerator, but our own curiosity. It's the willingness to ask why, even about things that seem obvious, like a spinning bucket of water. It's the courage to follow the mathematics and the logic, even when it leads to conclusions that seem to contradict common sense. This is the spirit of science. It's not about having all the answers. It's about the joy of the search, the thrill of peeling back another layer of the cosmic onion. So how can you apply these ideas to your own life? You don't need to be a physicist. The first step is simply to cultivate a sense of wonder. The next time you look up at the night sky, don't just see a collection of bright dots. See the light from stars that has traveled for thousands, even millions of years to reach your eyes. Realize that you're looking back in time. Ponder the fact that the space between those stars isn't empty, but is a dynamic, stretching fabric filled with dark matter, dark energy, and the faint afterglow of creation. The second action is to embrace uncertainty. Quantum mechanics teaches us that at a fundamental level, the universe isn't a clockwork machine. It's a game of probabilities, of potentialities waiting to be realized. We live in a world of possibilities, not certainties. And while that can be unsettling, it's also liberating. It means the future isn't written in stone, it is open. And finally, recognize the illusion of separateness. Quantum entanglement shows us that at a deep level, the universe is interconnected. What we do here can be linked to what happens elsewhere. This isn't just a physical principle, it's a profound spiritual and philosophical one. We're not isolated individuals. We're part of a vast, interconnected cosmic web. That was a summary of The Fabric of the Cosmos by Brian Greene. We've explored some of the deepest ideas in modern science today, but I have to be honest with you, a summary can only ever be a signpost. The real journey happens when you walk the path yourself. It's in the quiet moments of reading, when a particular story or a simple analogy clicks into place and suddenly you see the world in a completely new light. This summary is here to help you decide if this book deserves your time. If anything we've talked about today has sparked your curiosity or filled you with a sense of wonder, I urge you to grab a copy. Reading it isn't just about learning facts. It's an experience that can genuinely transform the way you see yourself and your place in this magnificent universe. The link to the book is in the description below. Also, if you found this journey valuable, please take a moment to hit that like button and subscribe to our channel. That way, you won't miss our next deep dive into another life-changing book from the billionaire's bookshelf. Your support helps us continue to explore these big ideas together. Let's keep growing, and let's keep wondering.